So where are we? We're starting a new chapter, chapter 5. So recall, let me remind you what we were doing in chapter 4. We were for the last couple of chapters, we started with the idea of slope. We were looking at slope, which the fancy word is derivative. The slope of the tangent line to a curve, tangent slope. We started with this definition that the derivative at x is a limit as u goes to x of f of u minus f of x over u minus x, right? Rise over run. Instantaneous is the limit of secant slopes. And then we learned things like the derivative of a polynomial is n times, the n comes down. We learned derivatives of sine, cosine, e to the x, log, all this stuff. We learned all of these things. Then we learned rules like the product rule, the quotient rule, the chain rule, all these beautiful rules, where rule is really shortcut, so that we don't have to go back to the definition every single time, right? That's kind of, now we're really good at derivatives and we know the applications of those subjects. So our next topic, our new topic is area. In the same way that slope has a fancy name called derivative, area has a fancy name called integral. And we're back at this stage where we're going to figure out from first principles what it means to compute integrals of complicated shapes. So let's do a very concrete example. I don't know. You guys got a function for me? Not too complicated. X squared. It's a little too simple. How about 1 plus x squared or something? 1 plus x squared. Okay. From not 0. Let's do something more interesting. From 1 to 2. Okay. So let's think about what that means. X squared would be down here. So 1 plus that just raises us up by 1. And I go from 1 to 2, from 1 to 2. So I want to understand our goal is this area. To figure out what this area is. All right. And we're going to approximate that goal in the same way that we approximated tangent lines, slopes of tangent lines by these secant lines. We're going to approximate that area in a systematic way. Last time we talked about how Fermat did it. His trick only works for very special functions, this being one of them. But we want something that'll work on any kind of function whatsoever. That's the full power of calculus, is when you can take, well, we can't take integrals of general functions, at least not in closed form, but never mind. So how can we approximate this area? Well, the dumbest approximation I can think of is the area is certainly no bigger than this box. So what are these points, by the way? This point is 1 comma, 1 squared is 1 plus 1 is 2, 1 comma 2. And how about this point? 2 squared is 4 plus 1 is 5. So 2 comma 5. 2 comma 5. Okay. So whatever this area is, whatever the true area is, it's certainly no bigger than the big rectangle, which has width 1 and height 5. So it's certainly no bigger than this 1 by 5 rectangle. And it's certainly no smaller. It's certainly no smaller than this little rectangle, right? Rectangles are things where it's easy to compute the area, width times height. And what we want to do is, from that easy calculation, be able to compute the area of anything. So what's the area of the width times height? Of the little rectangle, little green rectangle? Is that too green? Can you see that? Let's make that a little darker. Yeah, exactly. It's 1 by 2. It's got a height of 2. So it's 1 by 2. Okay, so the area, we've already sandwiched the area between 5 and 2. That's not very precise. Can we do better? All right, let's try to do better. So a better approximation is to start again with our picture. Here's 1, 0, 1. Here's 1, comma 2. Here's 2, comma 5. And instead of just using one rectangle, one from above, one from below, let's break it in to 2 rectangles. So if I were Okay. If I were to break this into two rectangles, and I could break it anywhere. I could break it like a little skinny rectangle and a big fat rectangle or something. But what's the most symmetric kind of? Let's keep it simple. KISS. Keep it simple, stupid. So what's the simplest place to put this point? In the midpoint. Let's make it equally spaced. Okay, so this is going to be 1.5, 3 halves. 3 halves squared. So what is f of 3 halves? This is 1 plus 3 halves squared is 9 quarters. 9 quarters is 2 1/4, so this is 3 1/4. So that's this point, 1.5, comma 3.25. And now for an upper sum, so the true area is at most these two rectangles here. Let me get a better. I don't know. You're not children. You don't need me to constantly change the color. Sometimes it helps though. Okay, so these two rectangles certainly contain the full area. So whatever the area of those rectangles is, that's an upper bound for the area, for the true area. So what's the width of these rectangles? A half. What's the height of this one? 5. And the other one also has width a half, but a height of 3.25. 3.25. You see that? Okay, and what about from below? What about from below? I can take this rectangle as a lower rectangle, and I can take this rectangle as a lower rectangle. So now, what's the area of this rectangle? What's the width? A half. And the height? 2. And how about this one? Width? A half. Height? 3.25. Okay, so what do these come out to? Go away. All right, no more color change. You guys see what's going on. What do these come out to? Oh God, what's the average of 5 and 3 1/4? Something. What is it? 4.125. What's the average of 2 and 3 1/4? The average of 2 and 3 is 1 1/2. And then I want to add another. So is it 1.62625? Something like that? 2.625. All right. Look, that's a little better. Our first estimate was 5 upper bound. Our lower bound was 2. Now our upper bound is 4. Our upper bound has come down a little bit. Our lower bound has come up a little bit. We're going to squeeze the area between these two values. Okay. Well, instead of breaking up into 2 rectangles, let's break it up into 4 rectangles, or 16 rectangles, or 237 rectangles. All right. We're going to break this up. So here's the idea. And this really is the fundamental idea of calculus. It's actually, we teach it backwards. It's integral calculus that was understood somehow before differential calculus, at least traditionally. Well, really, they were doing power series, which you don't do until Calc 2, but whatever. The idea is break a hard problem. And I think I said this on day 1. Break a hard problem into infinitely easy problems, and add them all up. Add all infinity of them up. Okay, so this is the sort of the key idea of calculus, is you take a hard problem, whatever it is that you're trying to work out in life. If you can break it into baby steps and solve each of the baby steps along the way, then in the end, that's you'll get the outcome you want. All right, so let's see how we would do this. So again, here's our picture. Here's 1, here's 2, here's the graph of 1 plus x squared. That's our function. Okay, y equals this is our graph. This point was 1, 1, 1, 2. This point was 2, 5. And now what we're going to do is we're going to break this into how many pieces? 4, 8, 237, n. Let's use algebra. Let's use the power of algebra and say we're going to break we're going to break into n pieces. Okay, so there's n pieces here, whatever the size of n is. What does each piece look like? So let me zoom in on this a little bit. This is 1 to 2. There are n pieces here. What's the width of each piece? 1 over n. The width of each piece is 1 over n because the full length of the interval is 1. So if you're going to take an interval of width 1, chop it into n equal pieces, each piece has width 1 over n. So if this point is 1, what is this point? 1 plus 1 over n, right? Because you've shifted over by a factor of 1 over n. What's this piece? 1 plus 2 over n. What's this piece? 1 plus 3 over n. What is this 2 is equal to 1 plus n over n. N over n is 1. What's this piece? 1 plus n minus 1 over n. Okay, everybody see that? So every location has a name. And now what we're going to do is above each value, we're going to put an upper rectangle or a lower rectangle. So let's work out what the upper bound is. That's called an upper sum. Upper sum. Now our function, for a general function, you have to figure out what value is the upper value and what value is the lower bound. What value is an upper bound for the integral and what value is the lower bound. Our function is increasing, so we can always use the rightmost endpoint for an upper value and a leftmost endpoint for a lower value. Okay, so an upper sum, in other words, an upper bound for the area is bounded above by, what's the width of this? What's this first width? 1 over n. What is the height? Yes, it's f of this right endpoint, f of 1 plus 1 over n, f of 1 plus 1 over n. Okay, that's that first little rectangle. How about our second rectangle? The width, again, is 1 over n. What's the height? F of 1 plus 2 over n, right? F of 1 plus 2 over n. And so on, until we get to the last one. Let me give myself a little room. So let's get one more. I mean, I think the pattern is clear. The width is 1 over n, f of 1 plus 3 over n. What's this last rectangle's height going to be? The width is 1 over n, the same 1 over n as all of them. Okay, and the last height is going to be, let's write it as f of 1 plus n over n. Because 1 plus n over n is 2, f of that is 5, but just to keep the same pattern. Now, it gets annoying to write things like this again and again and again. So there's as usual in mathematics, we like to compress information through symbols. How many of you have seen sigma notation before? Okay, about half. So I'm not expecting that you've seen sigma notation before. So let's remember, let's write this in sigma notation and you'll get the hang of it. You see, the only thing that's changing from one term to the next, sigma means sum. Sigma, this is a capital Greek sigma. This is a sigma, just means sum. Okay, what does each term, the kth term, so if we're looking at k will start at 1 and go up to capital N. It's these values that are the only thing that's changing from one term to the next. So this means the sigma notation, sigma as k goes from 1 to n, of what is a typical term, like when k is equal to 3, this is the term k is equal to 3, is this term, and k is equal to 2 is this term, and k is equal to n is this term. Okay, k starts at 1, goes all the way up to n. That's what this part of the notation means. And what is a typical term? What is the kth term? 1 over n. The width is 1 over n, and the height is f of 1 plus k over n. Okay. Let's check if you guys are following what sigma notation means. Should we do a quiz? It's a good time for a quiz. What's the sum as k goes from, I don't know, 3 to 7 of k squared sine of k? So what I mean is write this without using sigma notation. Without sigma notation. Doesn't mean I need you to figure out what sine of 7 is. You don't know what sine of 7 is. Just write sine of 7. But just to check if this is making sense. Give me a thumbs up when you got it. Let's. Give me a hand. Give me a hand if you are totally lost. You don't even know where to start. No. You can talk to your neighbor. K squared times sine of k as k goes from 3 to 7. So what's the first term? Right, when k is equal to 3, I get, so this is 3 squared times sine of 3. Plus, that's what sigma. Sigma means we're going to add up all these things. What's the next term? 4 squared. Yeah, 4 squared sine of 4. Okay, so give yourself a point for this one, give yourself a point for that one. Then there's a 5 squared sine of 5. Another point, 6 squared sine of 6. Okay, this is kind of silly. 7 squared sine of 7. So this quiz was worth 5 points. How many got 5 out of 5? Okay, good. Good, good. Okay, pass them on over. Trey, if you wouldn't mind. Great. All right, so it makes sense what this sigma notation is trying to accomplish? What would you rather write? 3 squared sine of 3 plus 4 squared sine of 4 plus 5, or just the sigma, right? Hopefully you're seeing the utility of this sigma notation. All right. Let's go back to here. Let me grab both of these. Okay, what is f of 1 plus 1 over n? Remember what f is. F of x was 1 plus x squared. So what is f of this thing? This thing is actually equal to 1 plus the square of what's inside, which is 1 plus 1 over n. You agree that this thing is equal to this? And what is this f of 3 over n? What is f of 3? F of 1 plus 3 over n? That is 1 plus the square of 1 plus 3 over n. Does everybody see that? Hari? Does that make sense? Okay, how about this one? This f of this last one. Nimmer, go ahead. Yeah, 1 plus n over n squared. That's the height, right? Those are the upper heights. Does that make sense? Everybody see that? Okay, can we write all of those now in sigma notation? So this whole thing is equal to, we've written all of these terms out. Here's the sigma notation version. Let's sum k from 1 to n. 1 over n is the width of each little piece, and the height is this function, which is 1 plus k over n squared. So these are different 1 pluses. This 1 plus is because f of x is 1 plus x squared. This 1 plus is because we're on the interval 1 to 2, and we start at 1. So this is a typical point in the interval 1 to 2 that's been chopped up into n equal pieces. Does that make sense? Those are two different 1 pluses. They're both 1 pluses. Okay. Well, let's continue the calculation. We have a sum as k goes from 1 to n, 1 over n. And now let's open this up. Let's open the square, multiply this out. So I have 1 plus. If I open up the square, I get 1 squared. That's 1 squared. I get the cross term 1 times k over n. And how many times do I get that? I get that twice. So that's 2 times k over n. And then I get the square of this, which is k squared over n squared. Does that make sense? Does everybody see what we did? Okay. Well, if we're going to add a finite number of terms, and then we're going to add all these things together, let's multiply through this 1 over n. Let's do one more thing, which is to multiply through the 1 over n everywhere. So let's simplify a little bit. This 1 plus 1 is 2, and I have a 1 over n. So that's 2 over n. Then I have a 2k over n and times a 1 over n. So this is a 2k over n squared. And how about this last term? K squared over n cubed. K squared over n cubed. Now I'm going to add these things when k is equal to 1, plus these things when k is equal to 2, plus these things when k is equal to 3. So I'm just adding a whole bunch of things. Is that not the same as first adding all of the first terms as k goes from 1 to 2 to n, then adding up all of the second terms, 2k over n squared as k goes from 1 to n, and adding up all of the last terms as k goes from 1 to n, k squared over n cubed. Does everybody see that? Everybody see why that's true? All this means, what does this really mean? This really means when k is equal to 1, I get 2 over n plus 2 times 1 over n squared plus 1 squared over n cubed. That's my first term. My second term is a 2 over n plus a 2 times 2 over n squared plus 2 squared over n cubed, and so on until the last term. The last term is with k is equal to n. And all this does is it says, oh, you're going to add up 2 over n, and you'll do that n times. And then you're going to add up 2 times k over n squared, and you'll do that as k goes from 1 to n. And then you'll add up k squared over n cubed, and you'll do that as k goes from 1 to capital N. Does everybody see that? So whenever you have sigma note, this is a general rule. Is if I have a sum of g of k as k goes from 1 to n plus h of k. So if I'm adding two functions of k, some function g and some function h, and I add it from 1 to n, or from any bound to any bound, that's the same as adding the first function up as k goes from 1 to n, plus adding the second function. Does that make sense? Is K? The K can be anything. Let's make this L. K is a dummy variable. You get to choose what variable you want to, what you want to call the indexing variable. Listen. This is all, we're just working out the upper bound right now. Yep. Yep. Okay, does everybody see that? So this is the sum that we got. Now, okay, let's continue the calculation. This is all continuing the calculation of the upper sums. If I have 2 over n, does this depend on K at all? It's just 2 over n when K is equal to 1, plus another 2 over n when K is equal to 2, plus another 2 over n when K is equal to 3. So this first term is 2 over n plus 2 over n plus 2 over n. And how many times are we doing this? 2 over n. How many? N times, right? Capital N. So there's n times. Well, that's easy. That's just n times this thing. Okay, so that's this first term. This second term, every value, there's a 2 over n squared times k. So there's a 2 over n squared times 1. There's a 2 over n squared times 2, plus a 2 over n squared times 3, and so on, up to capital N. There's a 2 over n squared times the sum. In other words, this is the same thing as, what I'm saying is that this is a constant. And if you have some function of k and you multiply it by a constant, you could just factor that constant outside. Does that make sense? If you have some function, so here's another rule. We're getting a couple of rules now, a couple more rules with sigma notation. If I'm summing some constant as u goes from a to b, okay? If I have some lower bound a and some upper bound b, and I have a dummy variable u, and I'm summing a constant that doesn't depend on u. It's too general, Yusuf, or it's okay? It's okay. What will we get? We get c times, we get c, and how many times do we get c? B minus a? B minus a is a good first guess. We'll get the wrong answer if we look at a being 1 and b being n. Because we'll get here that there should be n minus 1 times, but it's not n minus 1 times, it's n times. So this includes the endpoint. Yeah, there's a plus 1. This includes the 2 endpoints. I'll show you in a second how to figure out stuff like this, sort of systematically. So here's one rule. If you're adding up a constant, it's just a constant times how many terms there were, but the number of terms from a to b, assuming a and b are both integers, this is always indexing, this is always incrementing by 1. This summation notation always means you're incrementing by 1. So you start at some integer a, you increment up to an integer b, you'll get b minus a plus 1 terms, each of them having value c. Another rule that we just discussed is the fact that if you have some function g of w, I'm really trying to use as many dummy variables as possible from 1 to n or from a to b. Let's not overload the variables. If I have this sum and I have some constant that I multiply by every term in the sum, what am I writing? What am I going to write on the other side of this? C times, everybody see that? It's the C just pulls out, factors out of every term in this expression as W goes from 1 to capital N. Does everybody understand these rules? Do they make sense? All I'm saying is if you have if you're summing a bunch of things and you're multiplying them all by 17, you could sum them first and then multiply the whole thing by 17. Okay. So that's the second rule. And now I'll apply it for the third term. The third term, I have a 1 over n cubed that's constant, so I can pull out the 1 over n cubed. That's a constant, and I'm left with the sum of the first n squares as k goes from 1 to n of k squared. Okay, so far so good. Let's recap. let's recap what we got. Recap so far. What we know is that we're trying to evaluate this area from 1 to 2 under this parabola 1 plus x squared. We've broken it up into n pieces, and we've evaluated the upper sums. So this is definitely an upper bound. Whatever the true area is, it is upper bounded by this stuff. For any value of n, for any capital N, the area is bounded above by, so what is this? This is n times 2 over n. That's this first term. Yeah. Plus 2 over n squared times the sum of k, the sum of the first n integers, as k goes from 1 to n, plus 1 over n cubed times the sum of the first k squares. Sorry? Does that make sense? Can you guys see that? So far, so good? Anybody confused? Did I lose anybody? Dan, raise your hand for a second. Anybody lost? Then just raise it. Okay, Ying, take me back. Thanks, Dan. Works every time. Okay, when I took this 2 over n squared outside of the sum over k. Okay, so the point is we had a 2 times k divided by n squared. We're going to set k equal to 1, and we'll have 2 over n squared times 1. Plus, when k is equal to 2, 2 over n squared times 2. Plus, when k is equal to 3, 2 over n squared times 3. Let me write it out. Let me grab this and write it out. Let me try to convince you of this. And thank you for raising your hand, because I guarantee there are lots of other people who are just too scared to say anything. What does this really mean? When k is equal to 1, I get a 2 times 1 over n squared. When k is equal to 2, I get 2 times 2 over n squared. When k is equal to 3, that's a 2 times 3 over n squared. Then 2 times 4 over n squared. I wrote cubed for some ungodly reason. And so on, all the way up to 2 times n over n squared. Right? That's exactly what the sigma notation means. And all I'm saying is that there's a factor of 2 over n squared everywhere. Every single term here has a 2 over n squared in it, because this had a 2 over n squared in it. So if I pull that 2 over n squared out, I get 2 over n squared times what's left over. 1, what's left over? 2, what's left over? 3, what's left over? Capital N. And if I write this sum in sigma notation, there's this factor 2 over n squared out front, and then a sum as k goes from 1 to n of k. When k is 1, I do 1. When k is 2, I sum 2. When k is 3, I sum 3, and so on. So effectively, what I've done is taken this 2 over n squared and pulled it outside of the summation. Does that make sense? Everybody's with me? Ying, does that make sense now? Okay. Great. Okay, so this is the area. Now we have to figure out what happens when you sum the first n integers. So there's actually presumably apocryphal story about young Gauss. Gauss was like a little, you guys heard of this guy Gauss, Carl Friedrich Gauss, German guy, one of the most influential, one of the most important mathematicians of all time. So when he was a little boy, he was goofing off in school, and a teacher wanted to give him, something to busy him just to get him out of her way. And she said to him, add up the numbers from 1 to 1,000. Just sit there and go 1 plus 2 plus 3 plus 4 up to 1,000. All right, that should give me a couple hours, right? He's like 6 years old. How long is it going to take him to figure this out? Like, I'm good now. I can deal with the other children. He comes back 1 minute later. Here's the answer, miss. How do you do it? Obviously, he is actually an incredible computer as well. Computer used to mean someone who could do a whole bunch of mental arithmetic. But no, Gauss did something much more clever. He said, if this is equal to S, then here's another way to write S. 1,000 plus 999 plus 998, and so on, all the way up to 2 and then 1. Right? If I write the numbers backwards and I add them up backwards or forwards, I still get the same thing. Anybody object to that? No. So let's add them together. So if I add these two rows together, I get 2S. Here I get 1 plus 1,000. 1,001. Here I get 999 plus 2. 1,001. Here I get 998 plus 3. Peter's got it. 1,001. And I go all the way up to the last term, 1,000 plus 1. 1,001. How many 1,001s were there? We're going to get 500 because there's a 2 here, but how many were there already? There's the first one, the second one, the third one, up to the 1,000th one. So this is 1,000 times 1,001. That's really easy. 1,000 times 1,001, even I can do that. So twice S is this. So S is half of this. Half of 1,000,000 is 500,000. Half of 1,000 is 500. Can I go play now, miss? This is what 6-year-old Gauss did instead of detention. Okay? Yeah. Because I'm adding S and S again. I'm adding both sides. So here's S once, here's S a second time. So if I add that, that's twice the sum, whatever the sum is. Each term is 1,001, and there's 1,000 of them. So I got to divide it by 2. Everybody see that? So let's use that trick to say, now what about 1 plus 2 plus 3 all the way up to capital N? Well, if this is S, then we can write S again as N plus N minus 1 plus N minus 2 all the way down to 3, 2, 1. Everybody see that? And if I add these two together, S plus S, 2S, N plus 1 is N plus 1, 1 plus N, N minus 1 plus 2, N plus 1, N minus 2 plus 3, N plus 1, all the way up to N plus 1 is N plus 1. Right? The 1,001 that we got when N was equal to 1,000. How many of them are there? There's N of them. So if I take N plus 1 and I add it to itself N times, that's exactly N, that's the definition of N times N plus 1. So what is S? Yeah, you can multiply this out if you like, or you can just think of it as N times N plus 1 over 2. Yeah, makes sense. These are called, anybody know what these are called, these numbers? What is it? A series? It's a series is usually an infinite, you're adding up infinitely many things. These have a name, Sid? It's the summation function, but these numbers in particular. So when N is equal to 1, I get 1 plus 2 over 2. So the first term, so if you think about what we're doing, we're just figuring out what 1 is, and then what 1 plus 2 is, and then 1 plus 2 plus 3, and then 1 plus 2 plus 3 plus 4. What is 1? Well, 1 is 1. 1 plus 2? 3. Let's see. If I put in 2 here, I get 2 times 2 plus 1 over 2. Right? When N is equal to 2? 2 over 2 times 2 plus 1 is 3. Okay, 1 plus 2 plus 3? 6. They're not Fibonacci. That's a good guess. So if I take N, if N is equal to 3, I get 3 times 1 more than 3 is 4 over 2. 12 over 2? 6. 1 plus 2 plus 4. Well, the first 3 add up to 6. The next one is 4 more than 6 is 10. And what is 4 when n is equal to 4? I'm supposed to get 4 times 1 more than 4 is 5 over 2. 20 over 2. 10. You see that? These numbers have a name. They're called the triangular numbers. Because here's 1, and here's 1 plus 2, and here's 1 plus 2 plus 3, and here's 1 plus 2 plus 3 plus 4, and so on. Okay, so these are called the triangular numbers. Just FYI. Okay, so we've proved a little theorem. We've proved a theorem that if you add up the numbers from 1 to n, 1 plus 2 plus 3 up to n, which we can write in sigma notation as sigma, yes, sigma as k goes from 1 to n of k, we've worked out what this sigma is. This sigma is, that's exactly what this S was. S was the total sum. So this sigma is n times n plus 1 over 2. Does that make sense? Does anybody know? So we're not going to have time to prove this. Does anybody know what the sum of the first squares is as k goes from 1 to n? So this is 1 plus 4 plus 9 plus 16 and so on up to n squared. So let's see if we can see something. 1 is 1, of course. 1 plus 4 is 5. 1 plus 4 plus 9, 5 plus 9, 14. 1 plus 4 plus 9 plus 16. So 14 plus 16, 30, and so on. It turns out that the answer, anybody happen to know this? Say it again. That's a very good guess for the starting value, and that is kind of true. Raga? Perfect. n plus 1, 2n plus 1 over 6. Now look at the leading term. It's n times 2n over 6. Exactly as Hader said. So it's n cubed over 3 is the leading term, but there's an exact formula, which if you put in n equals 2, you get 2 times 3. 2 times 2 plus 1 is 5 over 6. That's exactly 5. Okay, let me leave you with one more formula. So this is something that we're going to need again and again, identities like this, in order to be able to evaluate sums of squares. How about sums of cubes? So if I take 1 plus 8, what's 1 plus 8? 9. 1 plus 8 plus 3 cubed, 27. 9 plus 27, 36. 1 plus 8 plus 27, what's 4 cubed? 64. 36 plus 64 is 100. Why is that happening? So I claim that the sum of k cubed as k goes from 1 to n is the same as the sum of k as k goes from 1 to n squared. So this is 1 plus 2 squared, and this is 1 plus 2 plus 3 squared, and this is 1 plus 2 plus 3 plus 4. What's 1 plus 2 plus 3 plus 4? 10. 10 squared is 100. All right, I'll show you why these things are true next time, and we'll continue the calculation. We have to finish the calculation.